Hi, I would like to talk about the problem ICPC team selection. So this was not a very difficult problem based on the CADIS rating, and most of you solved it quickly. The type of problem is greedy. That's a greedy problem. So this problem was about the following. It was about given a list of students who participate in the ICPC, it's the coach's task to form a team out of those students. And here it is assumed that a team's performance might be the median of the team's participants. So in the case of three students, the median would be the middle one. And the question asks you to find out, to select teams such that the sum of the medians of each of these teams is maximized. And so if you think about this, so here as an example input that was given here was if you sort this, right, for example 10, 9, 9, 8, 8, and 6, you'll quickly realize that the optimal strategy would place the students with a 10 and a 9, and maybe one of the students down here into one team, and to place these students here into another team, because this way we get so this team here would have a median of 9, this one would have a median of 8, and the total performance would be 17. So more generally, the strategy here needs to be to sort the scores, split them into three equal parts. Let's say one, first one third, and and then make it so that each team has one student here from the bottom third. Okay, and then from the top thirds, the optimal strategy is to place two students that are next to each other into one team. Okay, so there would be like one team here, then one team here, then maybe one team here, and so on. And here basically you have one student to uh, to complete each team. Let's let me quickly code that to show you what that entails. So in this particular problem, and to show that this in fact works. So in this problem, there were multiple test cases that were given. So each of them needed to be processed. Each test case first started with a number n, and that was followed with a line with the scores. So the scores were read, and need to split them, and they were all integers. And so these integers then needed to be sorted in descending order. And then after this, let me just show you that this here works. So then, after this, we needed to output to find those. We would basically pick from this S. We would start with the second one, and we would need 2n many, and we would take every second one, and of those that we select, we want to output the sum. Okay, so this the answer here would be 17, and let's try this. To show that this actually works. Okay, so this passed. Now, let's talk a little bit about this problem though. So even though this problem appeared to be pretty easy, um, it requires careful considerations. Generally, greedy problems in programming competitions, unless they are as trivial or as simple as this one, tend to be pretty hard. And the reason is that you have to be certain that the greedy strategy of assigning an optimal solution is in fact the best one. And technically, this is something that requires a proof. And I'd like to spend a few minutes talking about how one might prove for this particular problem that this greedy strategy here is optimal. And so I came up here with a proof, may not be the only one, but I want to sketch it briefly. So the first argument in the proof is I'm going to prove that when in sorted order, that the bottom third here, that within this one here, that all the entries here are in different teams. Okay. So in other words, that each team has exactly one member in the bottom third. And so these proofs would be done by indirection. So we would say, what if this weren't the case? Okay, let's say there were somewhere down here a C and a D that belong to the same team. Well, if that's the case, then in the top 2/3, there has to be one team that is entirely in the top third. So there has to be one team. Let's call it um, X, Y, and Z that would be in here. Okay, so in this case, this team, of course, would contribute Y, and this team here would contribute C to the overall sum. Well, if that's the case, then we could do better, okay, by basically making it so that by here in this case, by exchanging Z and C, okay. So if we exchange those here in this case, then the resulting would be then we could use Z would be Y plus plus Z, and that is greater than Y plus C. So this is the argument why there has to be in the bottom third, there have to be all different teams, and so one of the three team members of each team would be in the bottom third. Now the second part would be for the top 2/3. Okay, why is the optimal strategy for each team to be in a disjoint two student sections? Okay, so for this I would make the argument, well, what if this weren't the case? Okay, what if there were two teams that weren't like this? Let's say a team like A and B, and a team C and D. There could be others in here, but let's say that they were disjoint like this. Okay. Well, so in this case here, the since for the two it would be the lower of the two, the result would be B plus um, B plus D. Okay. Well, but in this case, then I could form two teams instead by placing A and C. Let me get this right. A and C in one team, and B and D in another team, and the resulting score here would be C plus D, and C plus D is greater than B plus D because here C is greater than B. This is in increasing order. So therefore, do this. So if this proof by contradiction, we assume that it weren't the case, and then we were able to show that this could not be optimal because we were able to create one that is better. And so therefore, these all need to be disjoint, and that leads to the split that I have shown. Greedy problems can be very tricky. Okay, a lot of problems that are not greedy, that require some search, either through backtracking or dynamic programming, they have a strategy that is greedy and that looks as though it might work, but if you try it, you will actually fail it. So that's why it's important for any problem that you suspect to be greedy to have a proof that in fact the greedy strategy is the optimal strategy in this case. Now, from a practical perspective, if you're really uncertain, don't know how to solve the problem, it might be good to give the greedy strategy a try. However, in practice, greedy problems are not very frequent in programming competitions, so they do occur. And so there's a risk that you waste time implementing the greedy strategy when the actual problem cannot be solved with it.